Welcome back. Today we finish up 5.1 Approximating Area, and primarily I will do some examples, some more challenging examples of Riemann sums. For the first example, consider a function f of x equals sine of 2x over the interval from 5 to 15. Let's make a midpoint Riemann sum with n equals 400. So the n represents the number of rectangles. So with 400 right endpoint rectangles. And I've listed here the steps that we will follow just as a reminder in order for us to find that Riemann sum. So let's begin. First, let's find the delta x, the width of every rectangle. So delta x is, well, I could call this b minus a over n. That's the difference of my two endpoints. So 15 minus 5 over 400. I have 400 rectangles. So 10 over 400, which is 1/40th. So every rectangle has width 1/40th. So next, let's find the sample point. Let's find the right endpoint. I start this by writing out my grid points. So the left endpoint is 5. So 5 plus 1/40th, 5 plus 2/40ths, 5 plus 3/40ths. I'll do one more. 5 plus 4/40ths. And I imagine these numbers sort of under my x-axis, and those are the grid points, the dividing points between my rectangles. But now I need the sample points, and I'm using midpoints, so I need a midpoint right there. That'll be my x bar sub 1, and a midpoint x bar sub 2, x bar sub 3, x bar sub 4. And what will those values be? How about x bar sub 1? So it is the midpoint between 5 and 5 plus a 40th. So I really need just half of a 40th, which is 1/80th. So that is 5 plus 1/80th. How about my second midpoint, right in between 1/40th and 2/40ths? So maybe I can see this as 2/80ths and 4/80ths. I get 3/80ths. 5 plus 3/80ths. Now, if this is 2/40ths, that's 4/80ths and 6/80ths. So between 4 and 6 is 5. So 5 plus 5/80ths. And maybe now we see the pattern. 1, 3, 5. 5 plus 7/80ths. What is my formula for x bar sub k in general? Well, it looks like I need to see how the subscript on my x bar compares with the numerator. That's the thing that changes. And the numerator goes up by 2's. 1, 3, 5, 7. So I think I'll want 5 plus something over 80. And with a little bit of thought, we need to double that subscript and subtract 1. 2k minus 1. All right, those are my midpoints. Number 3. Let's evaluate the function at those midpoints. F of x bar sub k. My function is sine of 2x. So I get the sine of 2 times 5 plus 2k minus 1 over 80. And I can simplify that a little bit. So let's do some basic simplifying. The 2 multiplies to give me 10 plus 2k minus 1 over 40. Okay, that is done. I've found the heights of all my rectangles. Last step, let's make the Riemann sum. So the summation as k goes from 1 to, how far does it go? It's the number of rectangles. 400. And f of x bar sub k, so sine of 10 plus 2k minus 1 over 40. And then I need to multiply times the width, which is 1/40th. And that is it. We have found the Riemann sum using midpoints. Next example. Find the Riemann sum for the function 1 minus x squared, that's the blue curve, over 0 to 1 with n right endpoint rectangles. So what's new here is that the number of rectangles is a variable. but it's the same process as before. We'll just see there's nothing terribly new. Delta x is right endpoint minus left endpoint over the number of rectangles, which I will leave as a variable n. So 1 over n. Every rectangle has width 1 over n. How about my sample points? Well, the grid points will be 0, 1 over n, 2 over n, 3 over n, 4 over n, and so on. I'm choosing right endpoints. So x bar 1, x bar 2, x bar 3, x bar 4. It looks like in general the kth sample point, the kth right endpoint is k over n. What's next? Let's figure out f of x bar sub k. So I'll take my function 1 minus, and I'll plug in the k over n in there. And there we go. And there is, I don't know if it's simplifying, it's something you can do. You can change this into 1 minus k squared over n squared if you would like. Last step, let's make our Riemann sum. It's the summation as k goes from 1 to n, in this case, just a variable. And the function is 1 minus k squared over n squared, and that gets multiplied times my width, which is 1 over n. And here again, it's optional, but if you would like to, you can simplify a little bit. You can expand the 1 over n. All right, we'll call that good and say that is our Riemann sum approximation. This looks like it depends on two variables, n and k, but really it only depends on one. And the great thing about this formula is if n equals 10, then I can just plug in 10 for n, and that'll give me the area of 10 rectangles. If I make n 100, this formula gives me the area for 100 rectangles. And 1,000, it'll tell me what is the area if I use 1,000 rectangles. Last example. And this actually builds on the previous one. In the previous example, we found that the Riemann sum for f of x equals 1 minus x squared over 0 to 1 with n right endpoint rectangles is this guy. So let's give this a name just to make it easy. We'll call this r sub n, the right Riemann sum using n rectangles. Let's actually figure out what is R4, what is R400, R40,000. Now to do that, we're going to use Desmos.com, and I encourage you in the homework problems, use Desmos to help you figure out these summations. When it comes time for the test, there will be problems that don't require you to go online and do things, but for the homework, definitely give this a try. Okay, I will go to Desmos and show you how to do this. Here we are at Desmos.com. There it is in the URL, desmos.com/calculator. And it brings you to a page that looks like this. We won't actually use the graph, so you can expand that to the right, give yourself a little more room if you want. Here's the trick. Start typing the word sum in there, S-U-M, and here's what happens. S-U-M. It turns into a summation, and the lower limit is given to you partially, and they like to use the index variable n. Well, we like k, so let's backspace. I'm going to change that n into a k. And you can see if you do things like make this 1, and I'll put a 50 on top. Exclamation point means it still hasn't finished the evaluation. What if I just put k there? Immediately the answer 1,275 appears. So the summation k equals 1 to 50 of k, well that's just 1 plus 2 plus 3 plus 4 all the way up to 50. That is 1,275. What if I put a 2k in there? You can see how immediately things doubled. Alright, here's the tricky part. Now, if I say the summation of 2k plus 1, what is it calculating? Is it calculating the summation of 2k and then adding 1? Or is it calculating the summation of 2k plus 1? And it's the first. I have to be careful with parentheses. Right now, it's only taking the summation of 2k. If I really want 2k plus 1, I need to put that whole thing in parentheses, and you can see the answer has changed. Okay, let's actually tackle the problem at hand. So I want a summation. K goes from 1 to 4. And let me look back at the PowerPoint slide. I want summation K goes from 1 to 4 of 1 over 4 minus K squared over 4 cubed. All right, summation parentheses 1 over 4 minus K squared. Now to get the square, I'm using the shift 6, the caret sign, slash for a fraction, over K cubed. And that gives me, whoops, that's not right. How about N cubed? How about 4 cubed? Finally, there we go. And we get a solution, 0.53125. So K goes from 1 to 4 of my expression, and there it is, which is just a little bit more than half, which seems like a reasonable answer. 0.53125. Okay, 0.53125. So if there were only 4 rectangles in there, their area would be about half. How about 400? Here's where we can do a neat little trick with Desmos. I'm going to open up a new line below it, and I'll type n equals 4. Equals 4. Then up above, I'll replace the 4 with an n. So n there, n there, n there. And you can see I have the same answer that I did before. 0.53125. But now, look what happens. I can change this n from 4 into 40, and immediately the new answer appears. Let's call it 400, and I get my new answer again. Let's say 0.6654, 0.6654. Let's make n 4,000. Let's make n 40,000. 0.66665. And you can see a pattern as n increases. Let's go from 40,000, 400,000, 4 million. So there it is. Look at that. When n is 4 million, the area under that, the area of all those rectangles together is 0.6666665, blah, 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 blah. Really close to 2/3. In fact, that's what it looks like it's going to. The limit as n goes to infinity of r sub n looks like it's going to 2/3. So the area under the curve there, in the end, ultimately, I bet it's exactly 2/3. We'll pick up that idea more in 5.2, but I've given you enough information today to do these problems in the worksheet and the homework, so get to it, and as always, please ask if you have questions.